Hello everyone. Today I'll be presenting the AIS-156 Thermal Shock Test, a key evaluation to ensure EV batteries remain safe and durable under sudden temperature changes. This test checks how the REIS reacts when rapidly shifted between hot and cold conditions, helping us identify risks like cracks, leakage, deformation, or thermal events. In this presentation, I'll explain the purpose, procedure, acceptance criteria, and common failures associated with AIS-156 thermal shock testing. The purpose of this test is to verify the resistance of the REIS to sudden changes in temperature. The REIS shall undergo a specified number of temperature cycles, which start at ambient temperature, followed by high and low temperature cycling. It simulates a rapid environmental temperature change, which a REIS would likely experience during its life. In short, this test ensures that the REIS can withstand rapid temperature transitions without compromising safety. Here is an overview of the complete AIS-156 thermal shock testing procedure. 1. Pre-test preparation, setting the SOC, safety devices, and ambient conditions. 2nd. Installation setup, placing the battery correctly in the thermal chamber. 3rd. Test procedure, thermal shock cycle, applying the required temperature cycles. 4th. Post-test checks and passing criteria, verifying safety conditions after testing. 5th. Failures and solutions, understanding potential issues and corrective actions. We'll now go through each of these stages in detail. Before starting the thermal shock cycles, we must ensure that the test conditions are properly prepared. SOC should be greater than or equal to 50%, though many OEMs prefer a higher SOC for testing. All protection devices must be active. The battery must be stabilized at 20 degrees Celsius plus or minus 10 degrees Celsius. As mentioned in the note, a standard charge-discharge cycle can be performed beforehand to compare performance. But since AIS-156 primarily focuses on safety evaluation, it remains optional. The next step is installation. As per AIS-156, the test can be conducted on a complete REIS or on relevant subsystems such as cells or electrical connections. However, if only subsystems are tested, they must still represent the safety performance of the complete battery. If the BMS or ECU is not mounted directly inside the battery casing, it may be omitted during installation. The most important point is that the battery must be securely positioned inside the thermal chamber. This ensures uniform exposure to high and low temperatures, allowing the test to accurately represent real conditions. Now let's move to the core part of the test, the thermal shock cycle. This table summarizes the full sequence defined in AIS-156. Step 1. The battery is stored for at least 6 hours at plus 60 degrees Celsius, plus or minus 2 degrees Celsius, or higher if requested by the manufacturer. Step 2. The battery is then transferred from high to low temperature within 30 minutes. Step 3. Next, it is stored for at least 6 hours at minus 40 degrees Celsius, plus or minus 2 degrees Celsius, or lower if requested. Step 4. These steps are repeated until 5 complete cycles are achieved. Step 5. After completing the cycles, the battery is stabilized for 24 hours at 20 degrees Celsius plus or minus 10 degrees Celsius. Step 6. A standard charge-discharge cycle is performed as per Annex 8, Appendix 1, if not inhibited by the device. Step 7. Finally, the battery is observed for 1 hour for any abnormal behavior. The note below highlights that higher high temperature levels or lower low temperature levels may be used upon manufacturer request. This slide shows a demonstration of how the thermal shock test is actually performed. On the left, you can see the thermal shock test profile, temperature rising to plus 60 degrees Celsius, dropping to minus 40 degrees Celsius, and repeating for several cycles exactly as defined in AIS-156. On the right, we have an image of the thermal chamber with the battery placed inside. The chamber shifts the battery rapidly between hot and cold zones, replicating sudden environmental changes that may occur during vehicle use. Together, these visuals help us understand how the test operates in real conditions. Upon completion of the thermal shock cycles, the battery is evaluated in accordance with the AIS-156 acceptance criteria. The REESS passes the test if none of the following are observed: electrolyte leakage, rupture for high voltage REESS, fire, explosion. Electrolyte leakage is checked visually without opening the battery. Apart from the AIS requirements, additional engineering checks can also be performed to assess real-world durability, such as looking for casing deformation, connector integrity, insulation condition, fastener stability, and proper BMS operation. After the thermal shock test, a standard charge-discharge cycle is performed, as described in Annex 8, Appendix 1. This step verifies that the battery still operates safely and correctly after experiencing temperature stress. It essentially acts as a functional verification test. Once the cycle is completed, the battery is observed for 1 hour at ambient temperature. This helps confirm that no delayed reactions, such as leakage, swelling, or other hazardous behavior, occur after the test. This slide highlights some of the common failure modes observed during thermal shock testing and their possible solutions. Issues such as electrolyte leakage from gasket shrinkage, casing deformation from temperature expansion, connector damage due to cracking, insulation degradation at low temperatures, and BMS or sensor errors caused by thermal shock can occur. These are typically resolved by improving sealing materials, strengthening the casing, upgrading connectors, using higher-grade insulation, and adopting automotive-grade electronic components. As mentioned below, if any failure is observed, a detailed root cause analysis must be performed, design improvements implemented, and the test repeated under the same conditions. This slide raises an important question. Is a custom thermal shock test allowed? As shown here, AIS-156 does not allow a fully custom thermal shock profile. Only minor adjustments are permitted, with test agency approval, such as using a higher high temperature level, using a lower low temperature level, increasing dwell time, increasing stabilization time. But the overall 5-cycle test structure cannot be changed. So while some flexibility is allowed, the core test requirements remain fixed under AIS-156. November Services provides complete AIS-156 thermal shock testing facilities and specialized engineering consultancy. Using advanced thermal chambers capable of rapid hot-cold transitions, we evaluate battery sealing performance, structural behavior, insulation reliability, and overall safety. We also support clients with test planning, instrumentation, documentation, agency coordination, and detailed failure analysis. With experience working alongside major EV OEMs and battery manufacturers, we deliver accurate and standards-compliant testing that helps ensure certification readiness. Thank you for your attention. We appreciate the opportunity to present our EV battery testing capabilities. At November Services, we are committed to providing accurate, reliable, and standards-compliant testing supported by expert technical consultancy. If you have any questions or need assistance with testing or certification, please feel free to contact us anytime. Thank you once again.